When a man swimming underwater hears a sound, he has difficulty telling what direction it's coming from. A dolphin can. And this precise directional hearing ability is highly useful to him and to us. When the need arose to quickly train a dolphin to work with aquanauts who would live under the sea for 30 days in the Sea Lab 2 experiment, the immediate choice for the job was Tuffy. Scientists working with Tuffy had become more and more impressed by his amazingly quick responses. He was learning new tasks in as little as 10 minutes and easily adjusted to new situations. Hardly anything scared him. He learned his tasks so well, in fact, that he would become angry at his trainers if they failed to carry out their end of things exactly right every time. While the aquanauts of Sea Lab 2 were living 200 feet below the surface of the sea, Tuffy carried tools down to them and brought back mail to the surface. Tuffy was also on standby duty to go to the rescue of any aquanaut who might find himself lost in the black water away from his seafloor habitat. In this drill, a diver simulating a lost aquanaut sounds a buzzer he carries. Tuffy, up on the surface, hears the alarm and goes to the rescue. Diving down to the Sea Lab habitat, he picks up a line and carries it out to the lost aquanaut, homing in on him with his directional hearing response to the buzzer being sounded and with his sonar. The aquanaut takes the line from Tuffy and follows it back to the safety of the habitat as the line reels itself in. Tuffy goes back topside to be rewarded for his good work. When you descend into the sea, the weight of the tons of water above you increases the water pressure at the rate of about 1/2 pound per square inch for each foot you descend. Man's body isn't designed to absorb the tremendous pressures that build up as we go deeply in the sea. This pressure causes increased amounts of nitrogen gas to dissolve in our bloodstream and body tissues. Unless a diver who goes deep is very slowly brought back to the surface, rapid decompression causes the dissolved nitrogen gas in his bloodstream and tissues to form gas bubbles, just as bubbles appear in a carbonated drink when you remove the cap and reduce the pressure. These bubbles can form in the blood and body tissues, including the brain, causing nitrogen narcosis and the bends, which at best is severely painful and requires the diver to spend hours in a recompression chamber. At worst, it can be fatal. All whales, including dolphins, can dive to great depths with no visible ill effects. While he is not breathing underwater as a human diver is, the dolphin does carry down a lung full of air. Why doesn't the nitrogen in this air dissolve in his blood and tissues when he rapidly decompresses and cause the bends, rupture of the deep, aeroembolism, and other conditions that affect human divers? Working with Tuffy, Dr. Ridgway set up an experiment to find out. At the time these tests were conducted, no one really knew to what depth a dolphin could dive. Dr. Ridgway set out to obtain scientific evidence of the maximum depth that Tuffy could dive, to obtain breath samples from Tuffy before he returned to the surface, and to photograph by a remotely operated camera the physical appearance of the dolphin at great depths. Now, after several months of work, Tuffy is diving in the 800-foot range. No one knew a bottlenose dolphin could go this deep. Today, Tuffy will try for 975 feet. Several pieces of apparatus had to be built to collect data on Tuffy's dives. The heavy cable being lowered has a protected plunger switch that Tuffy must press. His pressing this switch will turn off the buzzer, fire the flash gun, and operate the camera being lowered. Before reaching the surface after his dive, Tuffy has been trained to blow his breath into this funnel, which traps a sample of it in the attached container. Taking several quick breaths, Tuffy heads downward. The push-button switch at the end of the cable is his target. Far above, trainer Bill Sconce sees the light go out, indicating Tuffy has shut off the buzzer some 975 feet below. Tuffy stops off before reaching the surface and on signal blows his breath into a sample collector for Dr. Ridgway to analyze. One mystery that Dr. Ridgway is trying to solve is why Tuffy's chest isn't crushed at the awesome pressure of 975 feet. And even if he can survive it, which he obviously does, why doesn't he get nitrogen dissolved in his bloodstream and tissues? Analyzing Tuffy's exhaled breath shows the oxygen-carbon dioxide changes that occurred during the dive. How do they do it? Well, the mystery is solved. Here's a photograph of Tuffy as he looks normally. And here's a photograph of Tuffy at 975 feet. As you can see, his entire lung area is totally collapsed by the water pressure. His chest is designed to be compressible. The dolphin's body is actually so flexible, he can undergo this kind of a pressure squeeze without injury. And why doesn't he get the bends? Well, when his chest and lungs collapse, it blocks the normal process of gas transferring from his lungs to his bloodstream. So, since the air gases in his lungs can't enter his bloodstream, he doesn't get any increase in the nitrogen in his blood and tissues. Although he decompresses very rapidly by swimming back to the surface, there is no dissolved nitrogen in his blood and tissues to form gas bubbles. Consequently, no nitrogen bubbles, no bends. Some of Tuffy's huge cousins, like the sperm whale, can dive to over 3,000 feet and stay down for more than an hour. Apparently, their systems function the same way. Other sea mammals who are deep divers, such as the sea lion and the seal, obviously are adapted to withstand the effects of deep diving. Well, during the first 8 years that Tuffy and his friends worked with our scientists, what have they taught us? How have we benefited? First, the dolphin has become a domesticated animal. He has exceptional capabilities in the sea, especially in situations where man is least effective. He was proof that dolphins could be released into the open sea and would return when called. He has given us new approaches on the use of sonar that will result in the sea becoming a little less opaque to man. The dolphin sonar also has possible practical application as an aid to the blind. And he's taught us how he can dive down to the crushing pressures of the deep sea without harm. Knowledge that will be helpful as we seek ways for man to move deeper into the sea. As we gain knowledge of how his directional hearing works in water, we may be able to utilize this knowledge to improve man's directional hearing underwater. From the exhaustive investigation of his physiology and development of new methods of treatment of the dolphin's diseases, we have gained new knowledge that not only will help preserve the health of our animals, but will also be a direct benefit to man. Encouraged by our success with the dolphin, our scientists are broadening their studies of sea mammals and birds, as each has much to contribute. We're studying the killer whale, who appears to be just as friendly and trainable as the dolphin, the deep-diving sea lion, and the large stellar sea lion. And the workhorse of our accomplishments, our #1 sea teacher, has been this 270-pound bottlenose dolphin from the Gulf of Mexico. The knowledge gained from him helped our scientists train the team of dolphins working with us today. In the spring of 1970, Tuffy died of a rare bacterial infection, one never encountered in a dolphin before. But even though Tuffy is gone, the work continues with other members of the dolphin team, who recently were joined by a new little fellow. Researchers in the future will build on his contribution as they probe ever further into one of man's most challenging frontiers, the deep sea.